Welcome to the 20th lecture from chapter 8. In this lecture we will study BiCMOS NOT. It's a small recap of the last lecture in which we studied the general structure of a BiCMOS logic circuit, which contains a CMOS driver circuit in which the complete circuitry is CMOS based, and two transistors, namely this transistor was named as Q1 and this transistor was named as Q2. This transistor is Q1, this transistor is Q2, and we have this as the output terminal where we connect the output load capacitance connected to ground, CL. Right, in this lecture we'll study BiCMOS NOT. The structure is given. This is the PMOS array of a regular CMOS based NOT. This is the NMOS array. We know that there is only one PMOS transistor and one NMOS transistor, and this is the repeated NMOS array. We draw here the NMOS array once again, and this is an extra NMOS transistor which we connect in every BiCMOS circuit. The functionality is that when the input voltage in is 0 volts, we apply 0 volts here. This MP turns on and supplies here voltage that is equal to VDD, because PMOS is on, so the output is a logic high, whereas this NMOS M1 transistor is off and this MN transistor is also off, so both these NMOS transistors are off, right? But as we apply VDD on the base of this Q1 transistor, the base emitter junction becomes high, base emitter junction becomes forward biased, and here we get a voltage that is VDD, the voltage at base minus the voltage drop between base emitter junction, VBE. So that's great that we get VDD minus VBE here, a voltage that is slightly smaller than the voltage VDD that we get in regular CMOS based circuits, whereas this VDD is applied to the gate of this NMOS transistor, turns it on, and this terminal, the base terminal of this Q2 transistor is also at 0 volts. Of this Q2 transistor is also at 0 volts. This means the base is at 0 and the emitter terminal is also at 0 volts. This means the base emitter junction is not forward biased. So we get a voltage V output high is VDD minus VBE. This is what is explained here. Similarly, when the input voltage is VDD, this M1 is on and the same input is applied to this MN, and this is also on. So when this is on, the output here is not VDD, rather instead of VDD it is 0 volts here, because M1 is on. This means the output here isn't VDD minus VBE, because the voltage 0 volt here is not able to turn this transistor Q1 on, so the output is not VDD minus VBE, right? So let's see what the output is then. this 0 volts that we apply here, this 0 volt is also applied here. This means this M2 is also off. But look at this Mn, this is on because the input of this transistor is at 5 volts VDD. This means anything that is here at this point will be available at the output. So what is here at this base terminal? What is the voltage here? Right, the voltage here is whatever is the voltage at emitter plus 0.7 plus 0 plus VBE. So the voltage here is 0 plus the voltage drop between base emitter junction VBE slightly greater than 0. So VOL, V output high, for this BiCMOS not is slightly higher than 0. So these two are disadvantages, but we have to live with them because it gives better performance. As we studied in last lecture, it gives better performance for circuits where we have the values of CL that are very large. So for very large values of CL, BiCMOS circuits are feasible because they offer lesser delays. In our upcoming lectures, we'll keep on studying BiCMOS circuits. Thank you.